You know that feeling when you're staring down a deadline, just wishing you could somehow bend time?
Huh, absolutely. It often feels like a puzzle you can't solve.
Exactly. But it reminds me of this classic recreational brain teaser. It involves nothing but two ropes and some fire, but it somehow explodes into one of the most profound ideas in foundational logic.
We're taking the deep dive today into that very puzzle.
Hmm.
How do you measure exactly 45 minutes using only two one-hour fuses? And the key, as you know, is that they burn completely unevenly.
Right, you can't just cut them in half. The rate of burn is all over the place.
Precisely. So the length tells you nothing.
The classic solution is just so clever. You light both ends of the first fuse.
Right, and that immediately cuts its burn time in half. So 30 minutes.
30 minutes. And at the exact same moment, you light just one end of the second fuse.
Yep, so it's burning normally.
Then, when that first fuse sputters out at the 30-minute mark, you light the other end of that second fuse.
And because it had 30 minutes left, burning it from both ends now means it finishes in just 15 more minutes.
30 plus 15, 45 minutes. Perfect.
And that little trick, that physical process, is our gateway to this abstract set of fusible numbers, which we just call F. It's basically every possible time you can measure this way.
And our mission today is to show you how this simple rope puzzle connects to, well, the absolute limits of mathematical proof.
It's a wild ride.
Okay, so let's get into the math behind this. There has to be a deterministic rule that makes this work, right? One that ignores the rope's, unevenness.
There is. It's called the fusing operation.
Yeah.
If you light a unit fuse at two known times, let's say time x and time y, the moment it burns out is given by a really clean formula.
Okay.
It's x till y equals x plus y plus 1 all divided by 2.
X plus y plus 1 over 2. And that works every time.
Every single time. The non-uniformity it doesn't matter. The formula only cares about the start times.
So if we take our base case, time 0,
Yeah.
we can light both ends at time 0.
Exactly. So that's 0 tilde 0.
Which would be 0 plus 1 divided by 2, 1/2.
1/2. And now 1/2 is a time we can measure. So now you can use that. What if you do 1/2 tilde 1/2?
That'd be 1/2 plus 1/2, which is 1 plus 1 is 2, divided by 2 is 1.
And there's 1 hour. So you can see how we can just sort of recursively build up this whole set of numbers.
We start simple, but the possibilities just multiply. This is the foundation we're building on.
And before we get into the really wild structure of that foundation, I should mention this deep dive is supported by Embersilk.
Right. If you're a business or really anyone trying to figure out where AI agents can make the biggest impact for you, whether that's training, automation, or custom software, you should check out embersilk.com.
They really do handle the hard stuff so you can focus on the big picture.
Speaking of the big picture, this set F, it has some really surprising properties.
It does. The first is that all fusible numbers are what we call dyadic rationals.
Dyadic meaning?
It just means the denominator is always a power of 2. 1/2, 1/4, 3/8, and so on. You're never going to get a 1/3 out of this.
That gives it a very rigid, almost digital structure. But here's where my mind started to bend a little. The set F is what mathematicians call well-ordered.
And that's a profoundly important detail. It means there are no infinitely decreasing sequences of fusible numbers. The set is actually incredibly sparse. It's full of these huge, measurable gaps.
So after any whole number, like the number 1, there's always a smallest possible fusible number right after it.
Correct. But the gap to that next number,
Right.
it gets weird.
Okay, go on.
So above 0, the next fusible is 1/2. Simple. But above 1, the very next one is 1 and 1/8.
Okay, a bit more complex, but manageable.
But then above 2, the smallest feasible number is 2 plus 1 over 1024.
Whoa. So the complexity it explodes.
Yeah.
The denominator jumps from 8 to 1024. That has to be the key, right? That explosion.
That is the key. That complexity of the structure of those gaps is encoding something monumental. The order structure of the set F is actually equivalent to an ordinal number called epsilon naught.
Epsilon naught. Okay, for those of us who don't spend our weekends reading proof theory, what does it mean that a set of rope-burning times is structured like epsilon naught?
Well, epsilon naught is the proof-theoretic ordinal of Peano arithmetic.
Peano arithmetic. So the basic axioms for all of our counting numbers. Addition, multiplication, that kind of thing.
Exactly. The foundational system for elementary math. And this simple rope puzzle, by structuring itself like epsilon naught, actually defines the absolute limits of what Peano arithmetic can prove.
So you're saying the statement, there is a smallest fusible number above any integer n, is true?
It is true.
But you literally cannot prove it using only the normal rules of arithmetic. It's too complex.
It requires a level of induction that Peano arithmetic just can't handle. A recreational puzzle bumps right up against the boundaries of formal mathematical systems.
That is incredible. I think what this means for you listening is just, it's a powerful reminder that even the simplest physical rules can encode these staggering structures.
Right. Every basic interaction in our universe seems to hold these undiscovered layers of complexity.
They're just waiting for our curiosity and our ingenuity to come along and reveal them. There's always a deeper level of progress to be found.
A beautiful thought.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.